Hi. Now we're going to give you a third example for a sequential circuit synthesis. What is this example? This is another kind of a counter which counts in this order: 0, 2, 4, 7, back to 0 counter. We would like to design this. Now that's the word description, isn't it? From this description, I could design two different sequential circuit. One of them is going to have two memory elements in it. The other one is going to have three memory elements in it. So first one, three memory elements. Why I am saying so? I am considering that the highest number in here is 7. So if I use three memory elements, I can take into consideration the output of the memory elements is also output of my circuit, like this. You see, Z1, Z equals Z3 is equal Y1, Y2, Y3. So if I take, in this case, if I take this Z outputs as Y1, Y2, Y3, so I have got three memory elements. These memory elements output is going to change for each clock pulse from 0 to 2, from 2 to 4, from 4 to 7, from 7 to 0. So this is one of them. The other one that we are going to examine later on is two memory elements. We are going to use. So I explain this one later on. Do this one first. So three memory elements, that means there are three states, isn't it? Sorry, not three, 8 of course. Look at this. Okay, what happens is that means memory elements Y1, Y2, 3. Three memory elements. By three memory elements, we can separate 8 states from each other. But in here, I will be using only this ones when Z equals to this one, 0, 2, 4, 7. So one state is 0, second state 2, third state 4, and fifth state is 7. So when the clock pulse comes like that, we are going to change the states like this. So in this here, I have got 4 states. So that means the other 4 states, what are they? 1, 3, 3, 4, 5, 6. These are the other 4 states not being used. Right? Now where is my output now? My output is the same as Y. So these are small y's, also Z1, Y2, Z2, Y3, Z3. So then, from that state diagram, we are going to go to the mathematical model. So in this mathematical model, you see 0 here when the clock pulse comes 2, 2 when the clock pulse comes 4, 4 when the clock pulse comes 7. So the other states that I said already, 4 states, that means these 4 states, 1, 2, 3, 4. That means 1, 3, 5, 6 states. These are the states. We can never reach to that stage for this specific case. That means if you are not going to reach these states, your next state functions becomes don't care for these states, right? So after the mathematical model, what we are going to do is to do the design. So these are the steps. So this 3 I already explained. So this table is the same as this. From now on, what we are going to do, we are assuming that we are going to use JK type member elements. In order to do the JK type member elements, we've got to find the memory element input functions. There is no Z function, so memory element input functions, it's going to be J1, K1, J2, K2, J3, K3. I'm going to find these functions in here. So I cannot move this, so I wrote those. How I'm going to find all this? I'm going to use the inverse definition relation or excitation table. Okay. So in order to find J1 and K1 in terms of independent variables Y1, Y2, Y3, I am going to compare present states and next states. For the first JK memory element, this is present state, and this is the next state. By using this definition, inverse definition relation here, you know small y, capital Y. Small y, capital Y. Let's make it like that. For the first memory element, this is. Then by using inverse definition relation, you're going to find here J1, K1 function. Okay. So for the second memory element, that is J2 and K2, use a different color. My present state is Y2, and my next state is capital Y2. Present state was small y2, next state is capital Y2. So by using this definition, inverse definition relations, I am going to find the JK function and K2 function in terms of these independent variables here, Y1, Y2, Y3. So the last one is, maybe make it a different color. So Y3 here, small y3, and this is capital Y3, and find out this J3 and K3 functions. So like that. So if you transfer these functions to Carnot map, since our independent variables are just 3, so it's going to be 3 variable Carnot map. How many Carnot map we're going to find? That means transfer these 6 functions to Carnot map. Why it is 6? Because for the first JK memory element, I've got 2 input, J1, K1. Let's go in a bit. Here are J1, K1. For the second memory element, J2, K2 functions. For the last memory element, J3, K3. So if we transfer all these functions, J1, K1, J2, K2, J3, K3, this Carnot map. What happens is this now, come back a bit more. So you see there is a group of Kphi don't cares here. So if you look at in our function here, for each function I have got 4 Ks only. These are don't care, so let me write this. This don't care. So this K here is the JK memory input, isn't it? Don't confuse that K and that K. Memory input. So you see the small case don't cares. Small case. So this should have been small case, of course. Okay. Transfer it to here. So look at here now. We've got 4 case here, don't cares. But in the Kano map, I have got 6 case. Why is that? 4 of them is coming from here. The other 2 comes this inverse definition relation. We've got case as well, you see. So the origin of 2 small case comes from this definition relation. Therefore, we've got more case than 4, which are coming from this case. So when you transfer all this to Kano map, let's make it bigger and clear this. Then you're going to find the minimal functions corresponding to these memory element inputs. How you're going to find it? Easy, isn't it? If you choose this 3k is equal to 1, so it's going to be j1 equal to y2. So this all case consider equal to 1, so j2 is equal to 1. So these are the minimum functions that we found. Then we are able to draw now our circuit. If you know the memory elements inputs, you see J1, J1 is Y2, J1 here is Y2. K1 is, what is this? That one is also Y2. You see, here it is connected Y2. So J2 is equal to 1, J2 is equal to 1, K2 is also equal to 1, connected to 1. And J3 is Y1, J3 is Y1, it goes to here. And K1 is equal, K3 is equal 1, isn't it, that one? So it is connected to here. So as we said already, Z outputs are the same as Y1, Y2, Y3. So if you consider a box, so this dotted box here is our circuit design. This is the end of the synthesis. This one has got 3 flip-flops. 3 flip-flop realization of 202470 counter. Let's come to the next one. Here you are. In this, once again, the box is the same. In terms of input-output relation, it is going to be the same, isn't it? But what is inside is going to change. How it is going to change? Now we are saying we are going to count 0, 2, 4, 7, then 0. So in order, if we can consider those as states, so if there are different state is just 4, isn't it? In order to represent 4 different states from each other, 2 variable is enough. So you might call A, B, C, D. These are the states. So to represent those states as state variables, so it's going to be 0, 0, 0, 1, 1, 0, 1, 1. So what does this mean? 2 memory elements. Output of those 2 memory elements cannot be the output of my circuit. Why is that? Because there are numbers that you can represent by these 2 memory elements is this, but I need number 7. So that means I cannot take the Z output as state variables. Z1 equal Y1, Z2 equals Z2 equal to Y2, Z3 equal to Y3. I cannot say so because there is no Y3. So what I am going to do, as I said, I am representing these states by ABC. After the coding is this. At that state, I am going to give the output Z as 0, 0, 0. When I come to this state, I am going to give the output this. So I've got three outputs here, Z1, Z2, Z3. So three output variables, I can represent the number that I'd like to see. So for this one, I can say that 1, 0, 0. For this one, 1, 1, 1. So now, what does this mean now in terms of design steps? So this is our state diagram. You see that's A, B, C, D. These are the codes for A, B, C, D. So these are the codes. That means state assignment, we have done it. What is underneath is the output functions. I have got three output functions. So let me draw it in different colors. So these are the output functions. So Z1, Z2, Z3. Why I put these functions in the state? Because it is a Moore machine, isn't it? Moore machine tells me that output functions depends on the independent state variables. Once you know the state variables, you can write the output. So what is this first one? Is make it different color. So this represents small y1, and this second one represents y2. So these are the independent variables. These are the dependent variables. From this state diagram, you can come to this now mathematical model, that is. So why it is a mathematical model? Because mathematical model was this. You've got the independent variables. These are the independent variables. And you're going to find next state functions, and output functions. So the mathematical model. After that mathematical model, what I need is only to find the memory element input functions. So I've got two memory elements, J1, K1, J2, K2. So how I am going to determine those? I am going to use inverse definition relation of JK memory elements and find out JK1. How I am going to do it? So I do it once more. So you're going to compare this small y1, this capital Y1, and determine this J2, K2 functions by using excitation table. In other words, inverse definition relation. So I'm not going to draw it once again because these are already been examined. So for the second one, we are going to compare this second column, small y2, and capital Y2, and determine this J2, K2 inputs once again by using excitation tables and inverse definition relation. That is not enough because I know the combinational circuit outputs are in two groups. One of them is the next state functions, not next state functions, memory elements input functions. The other group represent the output functions. So now I am going to use these outputs, three output functions Z's. I'm going to design those and also design all these memory element inputs. So this altogether is going to represent our combination circuit. So this same thing here, that's very easy. In order to find the minimal functions, you don't have to go to the Carnot map. You can directly show it. Let me show it to you as well. You see here, what is Z1? Z1 is the same as Y1, isn't it? Z2 is the same as 0, 1, 0, 1, Y2. Z3 is this, these are 0. So for this input, that means Z3 is Y1, Y2 multiplication. What is J1? If you consider this as 0, 1, it becomes Y2. So if you consider this one 0, 1, this becomes Y2. And all of them 1. All of them 1. If all k's is chosen as 1, so my function becomes J2 is equal to 1, K2 is also equal to 1. So the circuit is this. I can put it in a box now. That's the clock input. And our output is Z1, Z2, Z3. So at this output, I'm going to observe when the clock pulse comes 0, 2, 4, 7, and then 0. So we have two different circuits which does the same job. That means 0, 2, 4, 7 counter. So let's compare those two circuits now. In here I've got two memory elements or two flip-flops and one AND gate. This AND gate is 1, 2 input AND gate. In here I've got three memory elements, make it different color. Three memory elements or flip-flops and no gates. How I'm going to consider now these two. So you're going to consider the cost, that the money that you're going to pay for those elements. So in one integrated circuit there is two JK memory elements. So this is, I'll make it different color. This is one JK integrated circuit. For this one, although I am using only one AND gate, it is not available commercially, it is not available. So I am going to buy one integrated circuit in which there are 4 AND gates, but I will be using just one of it. So still I've got one AND integrated circuit. So that is the cost of this circuit, two integrated circuit. Let me make it a bit better. Two integrated circuit. Let's say IC integrated circuit. So when you come to this one, there are in each memory type integrated circuit there are two. So one for this, I need one IC for this. For the other memory element, although I need just one, I must buy a IC. So for this one, another IC I'm going to use. So it's going to be two integrated circuit required. So compare now this one with this one. So you're going to compare the cost of one JK IC plus one AND IC with true JK ICs. Which one's cost is less than the other, you're going to choose that circuit, that means. So that is the end of this video then.